So this talk is about two libraries that live over there. So some background, I work in a robotics lab, so I use Numpy quite a bit for various computational work. As we know, the Numpy system is very widely used. There are a lot of people who use it, a lot of libraries, a lot of support. But as I've discovered, and as many of you have as well probably, is that there are quite a few quirks in its kind of very core fundamentals that are kind of annoying. And after using the system for a bit, I gave up, kind of fixed the issues, and now, for me at least, the system is pretty pleasant. So my use cases and the things that annoy me aren't that unique to me. So hopefully if I talk about the libraries that fixed my problems, they might fix some of your issues also. Okay, so some administrative stuff. So the sources and the documentation live at the main project pages, which have URLs over there. This talk itself is linked there as well. And right, so there's plenty of documentation online, so I would like to not make this into a lecture. So I will try to organize this as a kind of top-level overview so you can see what the capabilities are, and then go read the documentation if you're interested in actually using the system. Okay, too much. Okay, so what am I complaining about? Right, so just a little bit of history. So before Python and NumPy, I was a heavy user of Perl and a project called PDL, which is a very similar computational engine, but kind of for Perl. So PDL has a very nice core design, and just a lot of the kind of basic design decisions are actually very pleasant. The main issue is that Perl is kind of in decline, and it doesn't have that many users. There isn't a lot of library support, and it's very unpleasant in that way. NumPy is very complementary. It has a lot of users, a lot of library support, a big community, but some of the core isn't as nice. So what these libraries actually do for the most part is simply to port the fundamental functions for PDL into NumPy. So if you've used PDL before, this is going to sound very, very familiar. Okay, so the main three areas addressed by the first library are just general nice manipulation of arrays to move dimensions around, to concatenate things, that sort of thing. And some nicer routines for very basic linear algebra and for broadcasting. And I will talk about all three. Okay, so let's do an example. So let's say I have two two-dimensional arrays, and I want to concatenate them along their rows. So I want to extend their rows. So, missing one? Oh, interesting. Okay, so I think I'm missing a slide, but that's okay. So let's say I have a NumPy array called AR32, whose shape is 3 by 2, so 3 rows and 2 columns. And if you read the documentation, the function to do this in NumPy is hstack. So H stands for horizontal. So there's also VStack for vertical, DStack for depth, and that's it. If you want anything else, I guess you have to figure it out. So if we give that function, so this is just a NumPy function, those two arrays, what do we expect? So we would like that first one. Do we get the second one? Do we get something else? And fundamentally, is anyone sure what the answer is? I'm guessing probably not, because these functions are surprisingly strange. So when I was writing this talk, I discovered this was actually a trick question, because what happens is that it actually barfs you because it doesn't want the arguments, it wants a list of the arguments. Fine, so if we give it what it wants, so we have an extra set of parentheses, so you get the output that you wanted. So it does indeed look horizontal, and it did what we want. Great. Okay, so let's extend this a tiny little bit. Let's give it 3-dimensional arrays. So I define an array of shape 1 and 3 and 2. So this is a 3D array. It has one extra dimension on the front. And so we can see that its shape is what we expect. And the same question. When we call hstack on it, do we get a nice horizontal concatenation that we expect? Do we get this vertical thing? Do we get something else? Does it barf? Again, I'm going to guess no one is sure what the answer is. So the answer is that. So I called hstack on it, and that is not horizontal. And unless you're an expert in the way NumPy does things, this is going to be surprising. And then, so I'm guessing this is familiar. So it hit a nerve for me, because I kept running into this over and over again. Right, so what if we give it one-dimensional arrays? So let's say I have AR3, which is a one-dimensional row vector of length 3, and then I have AR13, which is a two-dimensional matrix, but that's 1 by 3. So if I hstack the two vectors together, it does what we expect. If I take the two matrices together, it does what we expect also, but if I mix them, if I try to hstack AR13 to AR3, it barfs. So it says that it wants the same dimensions, which I guess you could make an argument that's reasonable. However, if you do the same thing with VStack, it works fine. So it's, and these are very fundamental core functions in the system, and I argue that they should not be this strange. So this is kind of an important question, so I'm going to get a little bit deep into what it's actually doing. So the fundamental problem is that the system is not internally consistent about which is the most important dimension, the first one or the last one. Kind of these numerical algebra systems have a fundamental design decision, which is if you have n objects of arbitrary shape, let's say ABC, and you stack them together, does the n go in the front or does the n go in the back? Either answer is fine, but it has to be consistent. So again, to kind of hammer this point a little bit more, let's say you have a bunch of temperature sensors somewhere, and you put them into an array. So you have a one-dimensional array called T1 that has temperatures in different places. So the shape of that is n locations, because that's how many sensors you have. So this is a one-dimensional array, so the locations are indexed by axis equals 0, so the first axis, and also axis equals -1. So this is one-dimensional, so it's the same axis. Now, let's say you extend this. So you have an array T2, which does the same thing, but over time. So now you have a two-dimensional array with locations and times. So you have a choice. Do you have an object of shape n times and locations, or the other way around? So if you were designing this, and you wanted to produce a system that was nice, whatever that means, you would want a couple things. So one thing I would want is consistent printing. So when I print T1, I get locations printed horizontally. So what I would like is that when I print T2, I still get locations printed horizontally. I can get times or whatever vertically, but I would like it to look similar. So that is what I wanted to look at. So the way NumPy prints things, that implies that T2 should have shape n times and locations, not the other way around. And this comes just from the way it prints it. NumPy could make a different design decision, which is to print one-dimensional objects as column vectors, but it doesn't. So I claim this is what you want. Okay, so another thing I want is the axis that refers to some property, like the locations, should be the same axis in both cases. In T1, the locations are the first axis and the last axis, so 0 and -1. For T2, the locations are in axis 1 and axis -1. So which means that if you want to have a consistent representation that says that when you want to know what the location axis is, if you count the axis from the back, then you can actually be consistent. So if in both cases, you can say axis -1 locations, and that's fine, it'll work either way. So those two things together imply that when you stick matrices together, you really want to put your n on the front, and when you refer to axes, you really want to count them from the back. And if you do that, then your world is going to be much more consistent, and you're not going to confuse yourself. And again, this is a design choice, so PDL actually does something different. It counts the axes from the front. It says that the horizontal printed dimension is the first one and not the last one, and it puts n in the back. So that is fine, that is a self-consistent worldview. The issue that is not obviously right is that if you read any linear algebra textbook, a matrix with n rows and m columns is is an n by m matrix. And yeah, I got this. Is an n by m matrix. And the way PDL does it is actually backwards. So you can't please everyone, but you really should be self-consistent. And the reason that HStack doesn't work is that it's not self-consistent. So what HStack actually does is it concatenates along axis 1. For a two-dimensional array, axis 1 is the horizontal axis, so that's okay. The reason one-dimensional arrays work in NumPy is that it has special case logic for one-dimensional arrays, but that's it. So if you give a three-dimensional array, you get the strange predictable behavior that you saw. And this is true of a whole lot of functions, of VStack and DStack and all the others. So, right, so what does NPS do? It steals the API directly from PDL, shamelessly. There are two functions, one called glue, which takes any number of n arrays arguments and an axis. And the axis has to be negative. So an equivalent to HStack, to how we think HStack should work, would be to give it a bunch of arrays and say axis -1. And then another function is cat, which takes a bunch of things, creates a new dimension in the front, and sticks them all together. So these are kind of simple examples. So you can take, you know, if you take two 3x2 arrays and stick them together horizontally, you get 3x4. You know, similarly, along the axis equals -2, so your three-dimensional cats work. You can mix things together as long as things are kind of internally consistent. And things work mostly the way you expect. So cat is similar. So, you know, so in these cases, I gave it two things. I can give it as many things as I want. So the first, so you get a 2 at the front, and the dimensionality of the rest of it is whatever you gave it. And should also say that this respects the broadcasting rules that I'm going to get into in a bit. And one of those says that you can add as many length 1 dimensions of the front as you need. And what that simply says is that one of something is conceptually the same as something. It's not a crazy thought. Okay, so there are a lot of functions in that area. I'm not going to get into them. Leave the documentation if you're interested. So another area that's kind of funny is just general linear algebra. So even matrix multiplication. So up until NumPy 110, which is not that old, the way you would multiply matrices was by calling the dot function. The dot product and matrix multiplication is not the same thing, so I'm not going to get into the strangeness that that produces. So in 110, they fixed it mostly by a new function called mapmul. It mostly works, but it still has weird corners. So for example, if you wanted to compute an outer product like that, it barfs. And I claim it should not. So I provide my own function to do multiplication. You can give it as many arguments as you want. It works for the outer product case. It supports broadcasting, that I'm going to get into in a bit. And it's just a nice replacement. And again, there are a couple functions in that area that work. Okay, so I keep mentioning broadcasting, so let me talk about this a bit. So just out of curiosity, how many of you have ever heard of this and know what this is? Everyone? No one? Okay, it's about what I expected. So first let me just talk about what this is, and then we talk about why we care about it. So this is a generic way to vectorize functions. So if you have a function that is aware of broadcasting, then when you define the function, you give it a prototype which tells it, is that better? Yes. Okay. Okay, thanks. Okay, it has a prototype, which means that when you define the function, you define the dimensionality of all of its inputs and all of its outputs, optionally. So when you call such a function, it can compare the dimensions that it expects, because you told it what they are, the dimensions of the objects that you gave it. If they don't match in some way, it'll barf, which is good, because it makes sure you didn't mess up. And the other really important wrinkle is that if you give it an object that has higher dimensionality than what it expected, it will call the function multiple times for each slice, and it will give you an array of the outputs. And if you have such a broadcasting aware function, that happens manually. That happens automatically. You don't need to actually write the loops to do the vectorization, write the checks. That kind of happens by the internal machinery.
So does that mean that it's able to be parallelized?
Okay, so the question was, does that imply that there's some parallelization happening? So the answer is maybe if the implementation does it. So the NumPy does support it in some functions, in a very small subset that most people don't realize that it does. I want to say that it has no parallelization. My implementations currently don't either, but as you can see, it's a very natural place to add it. So like you can, like especially if this is in C, you can easily add a OpenMP, a little OpenMP pragma, and they'll just do it. So I don't do it today, but you could. Yes, sir. I'll get to that. Okay. The question was about some implementation detail. But first, I want to actually give some examples so we know exactly what it is I'm talking about here. So let's just give an example of a broadcasting over a function. So let's talk about the inner product. It doesn't matter what it is specifically. It's just a linear algebra operation. It takes two one-dimensional vectors of the same size, and it outputs a scalar. So here's an example. If you take 1, 2, 3, 4, find an inner product of it with itself, and you get 30. So if you just give it a single vector, you get a scalar. Sorry, a single set of vectors, you get a scalar. But you can also create an array of shape 2, 3, 4, and then if you give it two of those, it will compute 6 different inner products. Each one will have length 4, which is that last argument. And you would get an array of shape 2, 3 in the result. So I really want to kind of drill down into this because I think this is important. So here's an actual array of shape 2, 3, 4. And then let's also define another array that's just a row vector. And so numpysane provides broadcasting where inner. So here I'm calling it. If I give it two of these 2, 3, 4s, there's the output of shape 2, 3. And then the first one is the 14 is the inner product of 0, 1 to 3 with itself. 734 is the inner product of 12 through 15 by itself, and so on. So if you give it identical shaped input, it'll do this, but you can also give it single. You can give it objects that have length 1 in the broadcasting dimensions, like A4. So if you compute the inner product of A2, 3, 4, which is a big vector, with just A4, which is just a single row, you get an output of the same shape, but they will be inner products of each row of the big matrix with the one row that we have. Okay, so here's the rules. Mostly it's what I described. I'm not going to get into this. There's a lot of documentation. Okay, so why am I talking about this? So if you read the NumPy docs, there's actually a very long, very detailed page that describes what this is. So everything I've just talked about actually is in NumPy. The documentation is very explicit, has lots of examples, does exactly what it is. The problem is that very few functions actually have any support, and so few that most people don't even know that this is a thing and this is an option. And it's too bad because it's a very useful technique. So, so my library provides two different functions. Two different functions to add broadcast awareness to any routine that you have. So one of them is in Python, one of them in C. The Python one is a decorator, like you said. And what the C one does is it generates a bunch of C code that you can then compile into an extension module, and most of things work as is expected. So if you have an inner product function, if you already have something called def inner something, and you have a function that computes one inner product, or anything, if you wanted to add broadcast awareness, you simply do that. You add a decorator, you give it the dimensionality of its inputs, so that says you have two inputs. Each one has one dimension, and it's n for both of them, which means that the shape could be anything, but they have to be the same. So and the output is a scalar. That's what that empty tuple means. And so now, and that's it. Now if you call this, and you give it a vector of length 5 and a vector of length 3, it's going to yell at you because the dimensions are not what you said they should be. If you give it an upper dimensional object, it's going to do vectorization, and things will just work. And you can apply this to any function you have, and it saves a lot of typing, makes things clear and nice. Yeah. So right, and the other one is a similar sort of thing. In C, in addition to doing broadcasting, it by its very nature has to do Python wrapping. So So you get a Python wrapped function that has the broadcasting logic in it. It's pretty convenient. Okay, so I'm going to switch gears now and talk about plotting. So there's plenty of documentation about the other stuff, and you can see what you need to see. Okay. So yeah, so let's talk about plotting. So as with the NumPy core, there's a dominant choice that people use to do plotting in NumPy, so matplotlib, obviously. So unlike the NumPy core, I'm not aware of anything that is broken with it. So if it's not something that's really annoying you actively, then maybe there's not a lot of argument for using my library. However, hear me out. So my main beef with matplotlib actually is that it's specific to Python. So in my day-to-day, I make lots and lots of plots, and most of them are not in Python, not in NumPy. They're completely separate and live in a separate world. I usually use gnuplot, which is a very old, let's call it stable plotting library. It's very capable, it's been around forever, it's fast, it's nice. But it's just the thing that makes plots. Sometimes I use it directly, sometimes I use front ends. Just because it is a thing that actually creates the plot itself doesn't mean that that is the tool you're talking to. So I'd like to keep using it, and matplotlib obviously because it's on backend. And that has a converse effect in that if you're a matplotlib user and you really like it, you think it makes the best plots in the world, you're still tied to Python. So if all of a sudden you move to a different language, you would have to do something else. And it just feels like there's no reason for it. Yeah, so there's that. Compared to gnuplot, matplotlib is actually fairly slow, and that's just because it was written 20 years later. Generally, you see that we're either plotting a lot of data or if you have to replot quickly. For example, if you have a 3D point cloud or something and you're interactively rotating it to look at it from different directions, it's a lot nicer with gnuplot. It just feels a lot better. Finally, matplotlib has an API that's arguably strange. They wanted to imitate the MATLAB API, which is fine if you're a MATLAB user. If you're not, then it just feels weird for no good reason. Okay, so I have this library, it's called gnuplotlib. It is a plotting library that uses gnuplot internally, but you make plots from NumPy arrays. So it's gnuplot, so it looks and feels the way I want it to. It's fairly quick. It's been around forever, so it has lots of features, lots of backends, and all the various things. I claim the API is better, and if you're a user of PDL, it looks exactly like that, because that's what it is a port of. And I should say I cheated here, because I wrote that too, but we don't need to talk about that. Okay, so just some design choices. So my library just has one function, it's called plot. So if you use matplotlib, it works by constructing the plot kind of a chunk at a time. So there's a whole bunch of functions you call, and then when you're done, you call, I think, show or something, and then you get your plot. So you can do that here as well, but we already have Python. Python is purely capable of adding things to arrays and then passing to lists and then passing them as arguments. So you can build up the plot piecemeal also if that is what you want to do. Finally, my library is a very thin shim around gnuplot itself, which means several things. Which means that it is as powerful as gnuplot is. So I don't interpret most of the things, so they just work. It means that I can mess things up if I don't touch them. And it also means learning curve is a little bit better, because it means that if you know how to tell gnuplot or any tool that uses gnuplot how to change colors in a point or something, then you already know how to do it here, because I just pass the data down directly. Okay, so now I just want to give some examples to sort of get a sense of the API, and then I will be done. So if you want to plot something, you just call plot. So here I defined a one-dimensional array that is a sinusoid, and I just called plot, and you get a plot. So I didn't ask for anything special, so you just get the defaults. So note that this is a two-dimensional plot, so each point is represented by two numbers. You have an x and a y. I only gave it one array, so it knows that it expected two things. It knows that it got one, and in that case, it knows that it should use sequential integers for the domain. So here it plotted it against 0, 1, 2, and so on. If I actually give it, So if I actually give it two different arrays, like here, then it will plot the two arrays in respect to each other. So sine versus cosine is a circle. So here there is a keyword argument at the end. So that's a plot option. Those apply to the whole plot at once. Square means auto-scale each axis together, so not independently. So if I did not pass that, I would get something that looks like an ellipse and not a circle. Okay, so, right. Yeah, that is what I said. So here we're representing each point by two numbers, an x and a y. You could have more if you wanted to. So let's say we want to have x, y in color. So if you do that, then you say tuple size equals 3. So you actually tell it how many points, how many values represent each point. There was a tuple size even without, but the default is 2. So if you're using 2, you don't have to specify it. You actually give it 3 arrays. So I actually gave it 3 arrays here. And then you tell gnuplot what to actually do with the numbers. So here I say lines, points, palette. That might look cryptic, but that's just how gnuplot does it. So if you know how it does it, that is not look cryptic to you. Right, so the underscore for with is because with is actually a reserved keyword in Python. So just to work around that, all my option names can have leading underscores that are ignored. So it's just an implementation detail. Yeah, so you can do that, and then you can see that your circle becomes color-coded. Right, so I should also say that you can have a lot more than 3 values per point. Like for example, you might be plotting error bars, right? And then in 2 dimensions, y error bars, you will have at least the x and the y. You will have, and then you will have either a delta, if they're even, they have the same size on both sides, or you can have, 2 extra points if they're skewed. So if you go to gnuplot, type help y error bars, it will tell you exactly the format, exactly how many values it expects, and all that sort of thing. Okay, so that's how you interpret data. So now let me talk a little bit about how you interpret different data sets, and then that's it. So the code and the documentation use the terms data set and curve interchangeably, so I'm going to do that too here. So the full explicit invocation is like this. So you say plot, and then you say curve, 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 and then you have keyword arguments that describe what you want to do with the plot. Each curve is a tuple with data and a dict describing things about the curve, so most of what you expect. And you can put curve options in the plot option as well, and those will act as the defaults for any curves that don't specify their own. So here's an example. So here I have 3 different curves. I plot a sine, a cosine, and a line. I label my x-axis and the whole plot. I say with lines, so that is the default one that applies to all of them that don't specify anything explicit, and the line does specify something explicit, so it's point size 1, so that is what you get. And, right, so that is what I just said. So broadcasting is fully supported here, which makes things really nice. So for instance, let's say I want to plot sine and cosine together versus the same domain. So I can do it like that. So theta is my one-dimensional x. Here I catered together sine and cosine, so that thing is actually a 2 by 100 matrix. So there's 2 different rows. One row has my sine data, the next row has my cosine data. So, plot is broadcasting aware, so it expects a one-dimensional thing. It's got a 2-dimensional thing, so it says, oh, I need to make 2 different plots. And that extends to plot options, to curve options as well. So normally the legend takes a string, so that is what the curve is called. So normally you give it a string, but I can give it an array of strings, and then that applies as well, and it just picks it up and labels it correctly. So I could do the same thing by actually passing tuples with sine and cosine and all that. It's a lot more verbose and effortful, and this is just nicer in a lot of ways. All right, so now I'm just show one fancier one, and we'll be done. So let's do that. So this is 3D. So it looks like we have two different spiral things. We have different colors. We have different sizes. So that is the code that generates that plot. So I'm saying plot 3D instead of plot. That is simply a shorthand. All it does is call plot with one plot option that says 3D equals true. That's it. The tuple size is 5 because now we have X, Y, Z, color, and size. So that with directive tells gnuplot what to do. So point size variable, i.e. take the point size from the data. Palette means take the color from the data as well. So Z size and color are clear. They're just one-dimensional row vectors. The first two, so cosine of theta is a one-dimensional row vector. NP array of 1 minus 1 is also a row of 2, but I transpose it, so it's actually a column vector. So cosine times transpose of array 1, 1 is an array, is a matrix of 2 rows, first one being cosine, second one being minus cosine. So I do that, I do the same thing for the sine, this thing broadcasts, I get two different spirals, and that's it. So there are a lot more examples. So this mostly just talked about the API. gnuplot is very capable. You can do all the things. It does all the things you would expect the plotting library to do, like 3D stuff, contours, histograms, all that stuff. There's a ton of documentation and demos on the website. Feel free to look at those. And yeah, so the full API docs are on the main page. There's a link to kind of a tutorial gallery type of thing that's in the first one. It's all linked together if you just go to the main page. It should all be pretty clear. And that's it. So that's the main page with all of the documentation of the talk and everything else. It's in Debian, so you can just apt install that, and it will just get everything you need. And that's it. Thank you. Questions? Have I made a pip package? I think so. Yeah, you just call it setup py dist upload or something? Is that it, or is there more? I believe I do. I don't actually use the PyPy repo, so I might have messed it up, but I do believe it's in there. Yeah. Anybody else? So the question was, should numpysane be inside the stock numpy? It could. I mean, there's no reason not to. I mean, one thing you can't do is just fix HStack, is because then that'll break everybody's code. I think it could be there. I haven't tried to do that. If you know the people responsible and want to talk to them about it, that would be fine. Yes, sir.
Does gnuplotlib support the superimposed plots where you have like a box plot and plot?
So the question was, does the plotting library support superimposed plot where so you mean you would have different plots kind of in this, more than one plot in the same window or something?
Two layers of the same data, let's say. Oh, this might look like a gnuplot, so my initial plot might be a box plot, and then on top of that I'll impose a violin plot.
So I mean, would that be different from something like this? So here I have two different data sets. But the,
different data sets, but one.
Yeah. So they're both lines, but that is a detail. So because, so if you look at this example, so here I plotted 3 different data sets, and the styling is completely independent, right? So here one is plotted with lines, the other one is plotted with points, but it could be, one of them could have boxes or error bars. So this was meant to illustrate that you can put styles into the keyword arguments, and then those are used as the defaults. But you can, every single data set could have its own width setting to do whatever you like. Well, so you would need to either explicitly pass it twice, or you can use broadcasting. You can just put it in once, and then when you're specifying your width line, give it an array. Then it'll just do it twice. Anybody else? All right. Thanks.